Mohammed Abouzaid from Columbia University. He got his PhD from the University of Chicago in 2007 under the supervision of Paul Seidel. And after that, he was awarded the Clay Research Fellowship. And with this fellowship, he was at MIT for 5 years. And after that, he moved to Columbia University. And he has many papers on Floer cohomology, Lagrangians, and symplectic manifolds, and mirror symmetry. And today he will tell us family Floer cohomology and mirror symmetry. Let's welcome him.
Thank you for the introduction. Thank you for the introduction, and thanks to the panel for the invitation. So I did something maybe a little bit untraditional, which is instead of talking about things that I've been doing for the last 4 years, I'm going to be talking about things that I plan to do in the next 4 years. So the idea is to basically go back to a strategy for understanding mirror symmetry that was introduced by Fukaya about 10 years ago, maybe 15 years ago, and was essentially thought to be too hard to be implemented, and see what we can do with modern techniques. So let me start with some discussion of mirror symmetry. This really can't see anything too precise in the beginning. But from a mathematician's point of view, there's basically 3 fields in mirror symmetry. One is what we call the classical mirror symmetry picture. This is kind of what the physicists came up with and asked mathematicians about maybe 25 years ago. And you can summarize it, very basic level. You have these 2 Calabi-Yau varieties. But for us, we'll think of one of them as being a symplectic manifold, and the other one we're just going to look at the complex structure. And the statement is that, first statement you encounter is that if you forget the gradings, the cohomologies of these 2 manifolds are isomorphic. And moreover, if you try to put the grading back in, you realize that it's actually not the degree by degree isomorphism, but rather what you're supposed to do is you're supposed to take the degree filtration on one side and the Hodge filtration on the other side. And that's how the degrees match up, which is something rather surprising from a mathematician's point of view. Now, this is really just a zeroth step, and you can go beyond that. And the next step you encounter is something involving, from the symplectic point of view, called pseudo-holomorphic spheres. Well, again, this is I'm not thinking of X as a symplectic manifold, so I don't want to say holomorphic spheres. So the correct analog is, let's say, pseudo-holomorphic. And that should correspond to some kind of theories of Y. So you should imagine that Y doesn't come by itself, but in some kind of family. And these, you can take these pseudo-holomorphic spheres and code them in some kind of holomorphism theory, which can then be reproduced on the other side. So this classical picture is just some complete mystery. Someone hands you 2 objects and tells you, compute this on this side, compute this on the other, and they should match up. Why? We don't really understand. So the next step was due to Kintsevich actually at the ICM2014 ICM, so that's exactly 20 years ago. So instead of explaining this mystery, Kintsevich decided to add an additional mystery to it. Okay, so wrap it in a further mystery. So he said that these isomorphisms, they come from something deeper, from some categorical structure, which at the time had just been invented. So on the symplectic side, there should be some category, the Fukaya category. Later in this talk, I will say a little bit more about what that is, but you should just take it as black box. That category is supposed to be equivalent to something that's been studied for a long time on the algebraic side, which is just categories of coherent sheaves. So if you aren't familiar with categories of coherent sheaves, imagine that your Y, so this is some variety, it's covered by some standard pieces, which are affine varieties. Affine varieties correspond to rings, and if you give me a ring, I can look at the category of projective modules. So if you take projective modules over each of the affine pieces and try to glue them into something gluable, what you will get is exactly coherent sheaves. So, as I said, this is a beautiful conceptual picture, but it still doesn't explain why we have this phenomenon. And the first, and it's really so far the only real geometric explanation we have for this, is due to Strong-Uriel and Zaslow. This came a few years after Kintsevich's announcement. And this is really something that satisfies me as a mathematician, and I think also many other people, which is to say that what should happen is that you take X, you build a Lagrangian torus vibration on it, and then you dualize this vibration. And when you do that, you should get Y. So why is this reasonable? I don't have very much time for the introduction, but I just want to say, if you have a Lagrangian torus vibration over, say, a base, then the tangent space of the fiber is canonically isomorphic to the dual of the tangent space of the base. So if you dualize the fiber, you get something, another fibration, so that now the fibers are isomorphic, the tangent space of the fiber are isomorphic to the tangent space of the base. And if I have a vector space that splits as a direct sum of two vectors of the same vector space twice, I can write down a stupid complex structure, which just takes one to the other, okay? And the other back to the first one with a minus sign. So this naturally has an almost complex structure, and you can do a little bit of computation to check that this almost complex structure is integrable. It comes down to this integrability condition for the notion of the symplectic form. And so, in a way, the hope is that this picture would make mirror symmetry into a tautology. You hand me a symplectic manifold, I think about it, I try to produce a torus vibration, I construct the mirror, and then everything above should follow. So, this talk is about how much we can get, how far we can get in proving this, improving these two versions of mirror symmetry, but really mostly this one, that's what I'm focusing on, from the geometrical. And I want to say two things. The first one is that the passage from 2 to 1, passage from Kontsevich's picture to the classical one, has seen a lot of work in recent years, and there are definitely lots of strategies for proving it. Maybe the name to mention so far, kind of with the most contribution is, again, Kontsevich with joint work with Kazarkov and Pantev, which basically describes a strategy that one can try to implement for recovering the classical pictures from the homological one. And the last thing that I want to say on the slide is that in the algebraic geometry section, there is a lecture by Gross and Sievert, who essentially have, let's say, a very algebraic point of view on what this geometric XYZ picture should look like. So far, it's not completely clear to me how to implement our understanding of the homological picture from there. Okay, so let me say something about an example. I won't say very much. The example that I want to take is that of the two torus. So this is kind of one of the simplest symplectic manifolds we could consider. Let's say that it has area 2 pi a. So I said that the classical picture was going to be something about cohomology groups. Well, the mirror of this two torus is an elliptic curve. So if you take the cohomology, then it's obviously isomorphic to the one of X. But that's, again, the statement, remember, was not about degree being the same, but rather degree being the same as Hodge filtration on the other side. And if you know something about the Hodge diamonds, you know that the Hodge decomposition of the cohomology of an elliptic curve looks like 1 on top, and then 1, 1 in the middle, and then 1 at the bottom. So if you take P minus Q, you see this 1 here, which corresponds to degree 0 on the other side. Then you see the Hodge classes, the PP classes, which have rank, which is 2-dimensional, which is exactly the rank of the 1-dimensional cohomology on the other side, and then the last guy. So it kind of matches up. And I'm not going to say much more about this, in part because there aren't many genus 0 curves, or many maps from S2 to the 2 torus, so at genus 0 there isn't much to say. So the next thing I want to talk about is the homological picture. So this was actually verified by Polishuk and Zaslow very soon after Kontsevich's statement. And their proof goes as follows. We know everything about curves on the torus. We know everything about sheaves on the elliptic curve. Let's just match them up. Okay? So what do we know about curves on the torus? Embedded curves are determined by a pair of numbers, which you can think of as the slope, P and Q. So you just write down your torus as a square, and you decide what slope you're interested in. On the other side, coherent sheaves also have a slope. The thing that corresponds to P and Q are the rank and the degree. Degree basically is 1. Anyway. That gives you a bijective correspondence between embedded Lagrangians and some kind of vector bundles, although OP is not vector, but anyway, some kind of sheaves. And then you just check that what are morphisms, these are supposed to be categories, so in addition to objects, we also have morphisms, which correspond to Floer theory. That's very easy to compute in this 2-dimensional case. You compute that it's exactly the same as objects. So that's great. We checked it. But of course, this is not very satisfactory. One reason it's not very satisfactory is that it's not going to generalize to any higher dimension. There is no symplectic manifold of dimension greater than 2 for which we can list all the Lagrangians. So this is not going to work. But there are other methods, and so in particular, there is a proof in the literature that appeared in a paper of mine with Ivan Smith, which in a way is much simpler. There's much less to check. So instead of looking at all curves, I'm just going to look at the curve in class 1, 0 and 0, 1. So I called them here section and fiber because I'm imagining that I take this 2 torus and I project it down to a circle. So take a fiber and a section. And on the other side, the section will correspond to the structure sheaf, and the fiber will correspond to the skyscraper sheaf at a point. So it's basically a trivial algebraic geometry exercise to check that every coherent sheaf on the elliptic curve can be expressed, well, not quite as a complex in these two, but rather as a summand of a complex in these two. But there's just some basic algebraic procedure that you can apply. So similarly, you can show on the symplectic side that in the Fukai category, every Lagrangian can be expressed as an algebraic cone, or rather a summand of an algebraic cone of the section and fiber. So you could do this by hand, but actually the way we prove this is we use a general method that appeared in a paper of mine in 2010, which basically tells you when a collection of Lagrangians has this property. When a collection of Lagrangians, this is called generating the Fukai category. And the wonderful thing is that in dimension 2, this criterion basically says, take your curves, cut the Riemann surface along the curve, and see whether you only have polygons. Okay? So if I take the fiber and the section of the projection of the two torus to the circle, and I cut along those two curves, I get a quadrilateral. And the theorem, or rather the general result, says that if you can do this, then everything can be reconstructed from these two Lagrangians. So by the way, I suspect very strongly that that's the result that I was supposed to talk about, but as you see from the tone of this talk, I'm not extremely happy with it, and I think it needs to be generalized, and so that's what I'm really saying here. Okay, and so the last thing that I wanted to say is that these computations, they still require a little bit of work, but the SYZ point of view is completely trivial. You really just take the naive projection from the two torus to the circle that I was talking about, and you try to dualize it, and you explicitly get that the dual of x, which is this mirror, is this quotient of C star by this action. Z goes to multiplication by a positive number. Now, if you know something about elliptic curves, you're of course slightly disconcerted by this, because this tells you that only one real dimensional space of elliptic curves that we get by this construction, but you can kind of enhance and make more complicated constructions to recover the others. So what I want to say is that this is the toy example, but we can go much beyond this. You should think of this, the two torus as it appears as the elliptic curve inside CP2. Okay, take a degree 3 polynomial in 3 variables. Anyway, and then CP2, and that's the hypersurface that corresponds to it. So Nick Sheridan, in his thesis a few years ago, proved mirror symmetry for all Claudia hypersurfaces. And he followed essentially this strategy that I tried to outline that we did for elliptic curves. Basically, you find some collection, you use some geometric intuition. Just like here, I said, well, let's try to find something that corresponds to the structure sheaf and this Kaskirper sheaf. So you do the same thing. You try to use some geometric intuition to try to find a collection of Lagrangians which should correspond to generators of the category of coherent sheaves. And then you do a lot of work. Okay? The work goes into computing a bunch of Floer theory groups, Floer cohomology groups on one side and multiplications, a bunch of sheaf cohomology groups, and you check that they match up. And when you do that, you've proved mirror symmetry basically for these two collections of objects, and then you need some kind of generation result, and that's okay, we now have a machine to prove generation results, even though it's not as simple as saying, cut your symplectic manifold into pieces. It's a little bit more complicated than that. But what I want to stress is the fact that you start with geometric intuition, but it doesn't give you the proof. And what I want is a proof that it just says, look at the geometry of vibration, you're done. Okay. So how are we supposed to do this? So let me be a little bit more precise. So this is the setup we have to consider, so I have to apologize for the technicalities. So X is a symplectic manifold, and it will be closed. I will postpone discussion of Fukai category further, but for now what I want to say is that the objects are Lagrangians, but you may have heard that you're allowed slightly more generality than Lagrangians, in particular you're allowed unitary local systems. So if you work over the complex numbers, this is basically just first cohomology with coefficients in S1, but we're not allowed to work over the complex numbers. The reason we're not allowed to work over the complex numbers is because we're going to define, for example, multiplication by counting some holomorphic curves. Now, there may be infinitely many holomorphic curves, so it doesn't make sense to count. So the first idea is to say, well, let's weight by the area. That still doesn't work because the series that you get doesn't converge in general. But now let's say instead of weighting by the area with an exponential term, let's weight with a formal variable. Okay, let's call that formal variable t. And now things do converge. And in fact, the convergence is the result of Gromov. Gromov says if you bound the energy of the curve, there's only finitely many, well, then there's a compactness result. So that corresponds to the fact that we're going to look at series with real exponents, because remember I said we're going to put the area of the curve in as the exponent, with real exponents, with the property that if you bound the size of the exponent, there's only finitely many terms. That exactly says you look at series such that the exponent goes to infinity, psi goes to infinity. So this field, because I'm allowing negative powers, that's why it's a field, it's called the Novikov field. And this will be the field of interest for us. So now when we talk about unitary local systems, we have to think about what is the analog of the circle over this field. And it turns out that, well, the circle is the set of points in the complex plane that have norm 1. So you have to figure out what is the norm here. And the norm, well, let me just switch to valuation instead of norm. There's a nice valuation here, which is every non-zero series has a leading order term. So you take the exponent of the leading order term. So norm 1 corresponds to valuation 0, so we should look at unitary elements, or those which have valuation 0. That's what I call U lambda here. So this is not, you should think of this, this is not additive. Okay? You can't add two elements in here because the A0 is non-zero, but it is multiplicative. You can multiply. So it's a ring, and so it makes sense to talk about first cohomology coefficients. So this is the field over which things are defined, and these are the objects that we're allowing. Lagrangians together with this extra data of the class in first cohomology. And the morphisms are Floer cohomology groups. And again, I'm not going to say what Floer cohomology groups are, but what I will mention is what I would like to think of as the fundamental theorem of Floer theory. So this is due to Floer, and it says the following thing. If you take a symplectic transformation that is Hamiltonian, so Hamiltonian means the following things. If you take a circle in your symplectic manifold, and you move it by this Hamiltonian flow, then you'd like to say that so you obtain, by sweeping, you obtain a cylinder. So the Hamiltonian condition is that the area of the cylinder is 0. And that makes, it's a reasonable condition to impose from a Floer theory point of view, because look, I was using areas of objects as coefficients in my definitions, and so when you impose this, you get a better behavior. So the statement is, if you have such a diffeomorphism, then given any two Lagrangians, let's call them L0 and M1, you can keep one of them fixed and move the other one. And Floer theory won't change. Okay? That's the basis for most of the applications of Floer theory, in particular applications of the form, there is no diffeomorphism which makes L1 disjoint from L0. Because if this group is non-zero, maybe that's the second fundamental theorem. This group is non-zero, then there must be an intersection. Okay, so this is the general setup that I want on the symplectic side. So now, what is family Floer cohomology about? So we need one additional piece of information. It's not enough to have the symplectic manifold. We need this Lagrangian torus vibration. So Lagrangian is just a property that the symplectic form vanishes and that the fibers have dimension equal to half of the real dimension of X. So this strategy, which, as I basically said, hasn't seen that much progress because it just seemed too hard, is due to Kenji Fukaya. I introduced it about 15 years ago. So the main point of the strategy is to define Y starting from X. Okay? So you define it as the moduli space of simple objects which are supported on the fibers. So I'll give a much more explicit description of this in a minute, but for now, that's how you should think about it. And now, if I take a Lagrangian, any Lagrangian in X, then what I can do is I can take the Floer cohomology of this Lagrangian with the fibers, or with the fibers with local systems, but let's just. So that gives me a group. In fact, it gives me a group at every point of the space Y, because Y is the space of fibers together with local systems. Well, a priori, this group, this vector space, they have nothing to do with each other as you move past from one point to the other. And the goal of family Floer cohomology is to show that, in fact, they do. In fact, to show that they are the fibers of a coherent sheaf. So for that, we will have to understand many things, such that what is the analytic structure on Y that we're talking about, and so on. So there, I'm listing the difficulties, because somehow the first time you encounter the strategy, the first thing you think is, it's just too hard. So what are the difficulties? The first difficulty is, when you define Floer cohomology, you really use this feature, this thing that I call the fundamental theorem, that you can choose a Hamiltonian diffeomorphism, and the Floer cohomology won't change. So what you do is, if you take two Lagrangians, you can just assume that they're transverse. And then when they're transverse, you carry out the construction. But when you're doing this in families, this doesn't make sense. There is no way that given a generic Lagrangian inside the total space of the torus vibration, I can make this Lagrangian transverse to all the fibers. Because, for example, if I could do that, then the projection to the base would have no critical points. And that's very unlikely to happen. So that's the problem of cosmos. And Fukaya addressed this very nicely in a paper in 2001 where he gave a strategy for what you're supposed to do. We will see that again later in the talk. I will just say the following thing. The main idea is that you take a very small cover of the base and then you choose perturbations that depend on that cover, on every element of the cover, which achieve transversality locally. And then you have to patch things together. So the next problem is the problem of convergence. So I already told you that what we're going to do is we're going to define this Floer cohomology by counting some kind of holomorphic disks. And if you're fixing one Lagrangian and one of the fibers, for example, you can just appeal to Gromov's theorem to get convergence. But now it's not enough, because you need convergence not at one point, but in an entire neighborhood. We're going to say that something is analytic, so we're going to write down some series, and a priori they're just formal series, and we need to check if they converge. So this was again addressed by Fukaya 5 years ago. In a slightly simpler situation, but that was basically the main idea was already detailed. So the next difficulty doesn't appear in this case of the torus, which I was discussing earlier. But it appears when you look, for example, at the K3 surface of the quintic threefold, which is that in reality you rarely encounter symplectic manifolds which have Lagrangian torus vibrations. In practice, the vibration has some critical fibers, some critical points which correspond to singular fibers, and we don't know how to define Floer cohomology for singular fibers. So this is probably the essential difficulty that we're hitting. Unfortunately, I don't have much to say about it. There's Fukaya has some ideas we've been discussing, but it's not clear what to do in complete generality. So what this talk is about is, what if we don't have singularities? We should be able to carry out this program in that case. So we use this idea of perturbations to define this family of cohomology. And then you do a little bit more work to, in fact, define a map of the kind of functor. You'd like to know what properties does this have. And so the point of this talk is that it has some pretty good properties, but so far there's no proof yet that it does everything we want it to do. Okay, so let me now talk about the mirror. So now things are going to get even more technical. So as I said, we can't work over the complex numbers. So instead, we have to have this notion of rigid analytic geometry, which appears here. So again, just imagine everything is over the complex numbers, but I have felt the need to be honest. So I said we're supposed to take the moduli space of simple objects supported on the fibers. On the other hand, I told you explicitly what kind of objects we're taking. We're taking classes, first cohomology classes, off the fibers. That's what this XQ is, fiber at the point, with coefficients in U lambda. And you just take the union over all of them. It turns out that they're Floer theoretically distinct. There's no problem. There's no identifications that need to be made. Now this is just a set. Okay? So you need to define an analytic structure of this. And the analytic structure, it comes from symplectic topology. It comes from what is called the Arnold-Liouville theorem. The Arnold-Liouville theorem says the following thing. If I take one of the Lagrangian fibers, and I take a nearby one, then what I can do is I can take a bunch of cylinders connecting one to the other in different homology classes. And by measuring the areas of these cylinders, I get a class in H1 with real coefficients corresponding to which homology class I took. And this map, which goes from a nearby fiber, let's say that my fixed fiber is at P and the nearby fiber is at Q, this map, which goes from the nearby fiber to first cohomology, is injective. In fact, it's actually an open subset of first cohomology that you get by this construction. So once you know this, what you do is you take not all these fibers, but just the ones living over this subset of the base, and you can embed it inside the first cohomology with coefficients in lambda star. So lambda star is the non-zero element of lambda. So every non-zero element has a leading order term. Okay? So that gives you the map from lambda star to R by just, well, the leading order term has an exponent. That exponent is a real number. And now if you multiply this non-zero element of lambda by t to the minus that exponent, you get a unitary element. So that's the map from first cohomology coefficient lambda star to this product. Now, what this means is we can embed a local chart of y inside, well, this first cohomology is just a copy of lambda star to the n. So now imagine for a second, I've told you that I can embed my space, if we're working with a complex number, in C star to the n. Well, C star to the n is a complex manifold, and every open subset of it is also a complex manifold. So I have a chart for a complex manifold, and things work in exactly the same way in this rigid analytic setting. Okay? You get these charts, they're called affine domains. They're naming because they're the analogs of affine varieties in this kind of geometry. And because they're embedded in lambda star to the n, regular functions on them, analogs of holomorphic functions, are just series. Well, you'd like to say they're like Laurent polynomials. But of course, there's some completion of Laurent polynomials, because there are more holomorphic functions on a domain than there on a domain in C star to the n than there are in the whole thing. But you can get all of them by taking a series and requiring the series to converge. So this means that if I'm claiming that I can go from the Fukaya category to some category of coherent sheaves, at some point such series have to appear. So there are two examples. Give me 1 second. So there are two classes of examples I want to mention. The first one is the most obvious one you could guess. You could guess that if you take linear symplectic tori, these are just the things obtained by R2n and taken the quotient by a lattice. Unfortunately, not every such linear symplectic torus will work for us, because I had to assume the existence of a Lagrangian torus vibration. And that basically says that there is an n-dimensional subspace of the lattice on which the symplectic form vanishes. So this is a non-trivial condition, and it ends up being codimension, well, essentially n squared over 2. But if you are in a setting where this condition holds, then you can carry out the construction that I'm about to explain, and you obtain a mirror, and you obtain some relation between the Fukaya category of these tori and the categories of coherent sheaves on the other side. But just so that you don't think that this is all we're talking about, there's actually other examples. And my favorite one is the Thurston manifold. The Thurston manifold is the first symplectic manifold which is not Kähler. It has first Betty number 3, so it's supposed to be even if it were Kähler. You can write it as a quotient of R4, you translate it in 3 variables, and in the fourth one, you do translation and some kind of shear in the opposite direction. So we notice that this space has 2 different Lagrangian torus vibrations. And if you apply this mirror construction to one of them, just work over the complex numbers for now, what you get is a primary Kodaira surface. In fact, what you get is the Kodaira surface, which is diffeomorphic to this Thurston manifold that you started with. And this surface has the property that it is a complex manifold, which is not Kähler. So it's a nice instance of mirror symmetry in the non-Kähler setting, where you swap the existence of the symplectic form for the existence of a complex structure. But there's another Lagrangian torus vibration, and when you carry out the construction of this other vibration, what you get is an abelian variety. In fact, what you get is a product of 2 elliptic curves. So when you first encounter this, you think something is wrong, because any algebraic geometry will tell you that there's a very, very large difference between the derived category of a Kodaira surface and the derived category of an abelian variety. That's because there is some additional twisting that is taking place. So there's some non-trivial germ, whatever that is, I'll say a few words later, on this abelian variety. And so this twisted variety is supposed to be equivalent is supposed to be your actual mirror. So not only do we get an example of mirror symmetry in the non-Kähler setting, we also get an example of the fact that manifolds don't have single mirrors, that you can get many of them appearing by different Lagrangian torus vibrations. Okay, so now I can state the main result, or what one can prove so far. So let me assume, this is a technical assumption, I don't know a single case where it's actually not satisfied. Assume the second pi 2 of the base is 0. So then, one can define a class in the second cohomology of y with coefficients in O star. O star are invertible functions. So basically, you take a cover of y, and then for every triple intersection, you have an invertible function. And what you're going to do is you're going to use this invertible function to twist the notion of compatibility of modules over rings of functions. So this class, it measures the obstruction of the existence of the Lagrangian section of the original vibration of x. And here I said which is pinned, because that's actually the honest truth, so there's some additional twist, additional abstraction there. But if you take this class, then you can twist the notion of coherent sheaf, and then the result says that there is a faithful functor from the Fukaya category to this twisted category of coherent sheaf. So what does that mean? Well, that means that if you give me a Lagrangian, I can assign to it some object of this, an object I will call C of L. Okay, this is some twisted sheaf. Again, ignore twisting, let's say it's a sheaf. And moreover, I can do something more, which is I can take the Floer cohomology group of a pair, that's some morphisms in here, and I get a morphism of sheaves on this side. That's good, that's this map here. And this map satisfies some good properties, it's compatible with multiplication and so on. Now, I said that it's faithful. Faithful means this map is injective. So how do you prove this map is injective? That's what I will spend the next 15 minutes on. You prove it by building a map in the other direction. Okay? And checking that the composition is homotopic, well, the chain level is homotopically identity. So it's fairly clear that we should expect that, in fact, these maps are isomorphisms. And I've been trying. I think it's going to take quite a bit of time. It's actually a very good measure of how well one understands family Floer cohomology to see whether we can manage to prove that this is always fully faithful embedding. I do want to say that there are many, many, many situations where this is enough. Okay? If you take X to be, if you take Y, it's better to talk about Y. If you take Y to be an abelian variety, then just the knowledge that this functor is faithful tells you that this functor is in fact an equivalence. So there's really very little to do in that case, but I'm interested in the method, I'm interested in the machine and trying to develop it further because it's going to want to apply in situations where it's not going to be so easy, as easy as in the abelian variety case. Okay, so now let me say something about Lagrangian Floer cohomology. Or rather, I'll do everything in this family setting. So we take a Lagrangian next. And as I said, we don't really know how to do Floer cohomology when things are not transverse. So what I do, you take a small subset of this base, the base is Q, and then you can choose a Hamiltonian diffeomorphism which makes the Lagrangian transverse to all those fibers. So now the Floer complex, which is the complex whose homology is Floer cohomology, is defined as a direct sum over all the reg equal to the number of intersection points of, well, just a copy of the field over which we're working, that's this lambda. So this by itself is not invariant. We need the differential. The differential comes from the simplest kind of holomorphic curves that you would consider that involve the Lagrangian L and the fiber. So what you do is you take a disk, and on the upper part of the disk, you put L as your boundary condition. On the bottom part of the disk, you put the fiber as your boundary condition. And at the 2 points where they meet, well, you should have a place where you should put a condition that requires it to map to an intersection point of the Lagrangian with the fiber. So that's what this notation is about. So if you give me X and Y, which are intersection points of the Lagrangians X, Q, and L, then I can consider the moduli space that maps from the disk to the symplectic manifold with these boundary conditions satisfying some PDE equation. So the differential in the Floer complex can be expressed as follows. So it's going to have, here I have, my Floer complex has a basis corresponding to the intersection points. So if I write down the differential, it's going to have some matrix coefficients. The matrix coefficients for X and Y are a sum over all elements of this moduli space of the following expression. So I take this U, which is such a disk, I put a plus or minus sign by some rules which I definitely do not want to explain. Then I take T to the energy of U, the energy is just the area, and then finally this B is going to appear. And so the way it appears is that B lives in first cohomology, and I want to think of the boundary of my disk. So I have part of the boundary of my disk that is a path along the fiber, and I want to think of it as giving a first homology class. And I compare the first homology class with this first cohomology class and get a number. Now the reason the notation is kind of multiplicative is again because B lives in this first cohomology coefficients in U lambda, and U lambda has a multiplicative, you multiply element of it. Maybe the last thing to say is that, of course, this path does not have a canonical homology class, you have to make some choices, but that's kind of secondary to the construction. Okay, so the ideal thing would be to say that these matrix coefficients are actually regular functions. Okay? But they're not. They're unfortunately not. So I will illustrate it with this toy case, which is just to take a cylinder, I draw this Lagrangian, and my fibers, this is my reference fiber, and this is another fiber which is nearby, and I'm trying to understand how does the Floer differential vary as I move the fiber from P to Q. Okay, so well, the Floer differential for XP, XQ somehow, I decided to do that first, is the contribution of this strip, this whatever. You can imagine that if you shape this around a little bit, it looks like a disk with one Lagrangian boundary condition on L and the other one on this fiber. And it's supposed to contribute by its area. So if I try to understand this area in terms of the area of the corresponding disk with boundary on XP, okay, then what I get is that the difference between them is exactly the area of this quadrilateral. Okay. So now I think of this area of this quadrilateral as a function that depends on Q. So it varies as I move this fiber. Over here it's 0. As I move it, it changes. Now this function is not analytic. It cannot be analytic. Because, look, I could take my Lagrangian and I could perturb it by a C-infinity perturbation. On this sheet or on this sheet. And I would change it by a C-infinity function. That looks nothing like the kind of regular functions we were allowed. We were only allowed things that have these power series expansions. But that's okay. Because what I can do is I can express the area here, the error, the changing area, as follows. So first I fix this reference fiber in the base. Okay? Then I take this upper sheet and I look at the area below it. And I take this lower sheet and I take the area below it. That's the two real valued functions, fx and fy, that appear in this lemma. Okay? And I take the difference between them. Okay? T to the fx minus fy. In this case, this difference between them accounts entirely for the difference in area between this and this. So when you multiply by it, or rather by its inverse, you get a constant. You get a constant function, which is just the area of this strip. So now this might suggest that you always get a constant function, but actually it doesn't work like that, because if you look at an example like this, and you carry out the same point of view where you fix this reference fiber, you try to correct for the area of the strip as you move from P to Q by kind of subtracting the area below this upper sheet from the area below this sheet. What you get is, instead of a constant function, you get the constant function plus whatever area the cylinder has. Okay? But when I told you about the analytic structure on this moduli space, what I said basically is that these areas are exactly the holomorphic coordinates you have. Okay? So that says that after you multiply the contribution of the Floer differential by this function, what you get is something honestly analytic. And once you have this, you immediately conclude that you are in the realm of algebraic geometry. At least locally, you can produce these perfect complex whose fiber is isomorphic to the Floer complex. That just has to do with understanding how area changes. Okay, so I don't have very much time, so I have to go a little bit. This is the main point I wanted to say, because this is why rigid analytic geometry appears here. So I will want to say something about how you go from how you actually build these sheets. So I already said that what you should do is you should take a triangulation of your space. Okay? At every vertex, you do the construction that I just explained. You choose a open set near that vertex, and you build this complex in which you use that regular function for your differential. So then you'd like to know what happens when I go from one vertex to the other. So what you should have a map of complexes. And this map, it basically comes down to what I call the fundamental theorem of Floer theory, which is invariance. So, but we unfortunately have to do this at the chain level. If we did it at the level of cohomology, then we would basically be done. We build these maps, we show they're compatible, and then it's over. But if you want to prove the theorem that I stated at the beginning, well, in the middle, rather, the fact that we have this faithful embedding, you can't stop at this stage. You have to work at the chain level, and then there's some higher homotopes that you have to associate to every cell of your triangulation. Then somehow, if we were not trying to worry about convergence at every point, this would be relatively standard, but it takes quite a bit of work to make sure that everything converges. You always get these series that are not just formal series, but in fact convergent. Okay, so this is how you go to the global picture. And then you can map from Floer cohomology to the sheaf cohomology. So this sheaf cohomology is basically, in the Czech model, is a direct sum of a bunch of morphisms that are associated to every subset, to every cell of your triangulation. This map is exactly, kind of the spirit of it is the same as before. You again have some kind of parametrized moduli spaces, except now they're parametrized by the actual cells of the subdivisions. In fact, they're parametrized by truncations, but let's just ignore that for a second. Now you can build a map, that's what I label in blue here. You could build a map in the other direction, which are now parameterized not by the cells of the subdivision, but rather by the dual cells. That's what I draw in blue here. So if you take the product of the cell and the dual cell, then you can take these strips that are drawn in blue, the ones that are drawn in red, and you can glue them together. When you glue them together, that forms an annulus. And that annulus has Lagrange's boundary condition on some fiber. And then you shrink the inside of the annulus to a point. And when you do that, you get a disk with one marked point and a constraint. But if you think about it, the constraint is that the point has to go through some fiber. But the fibers altogether give the whole space. So this is not a constraint at all. Okay? So therefore, this is the identity on Floer cohomology. And people who have seen discussions of this kind of generation criterion will recognize this kind of argument because of the name of the Purdue relation. Except that in other places, it was kind of embedded in an enormous amount of homological algebra, Hochschild cohomology, and things like that. Here, it's embedded in an enormous amount of, well, I guess, family Floer cohomology. There's actually one small subtlety here, which is that I just went from saying product of a cell and a dual cell to now saying that it's something parameterized by the whole space. So if you actually want to make this argument correct, you have to decompose your manifold as a product of cells and dual cells. And this is probably classical, and can be done using the dual of the barycentric subdivision. So this is just some pictures. I'll be done in just less than a minute. So this is some triangulation. This is the dual of its barycentric subdivision. And if you stare at it very hard, you will see that you can write every cell of the dual barycentric subdivision as a product. And the picture is like this. So these are products of the point with a truncation of the dual cell. This is a product of a point with a truncation of the original cell. And these are products of two intervals, which happen to be exactly cells and dual cells in dimension. Okay, thank you very much.
Are there any questions? Okay, if not, let's thank our speaker again. Here's a gift for Mohammed from the ICM organizers. We'll take a 15-minute break.